Let's jump right into this explainer, okay? If you're a student sitting in math class right now staring blankly at the whiteboard and thinking, when on earth am I ever going to actually use this in real life? Well, listen up, because today is entirely for you. We're looking at May 4th. On the surface, it's just a regular spring day, but it's actually one of the most incredible, almost magical dates in all of math history. It's the date that secretly powers the modern technology you and I use literally every single day. On this one specific day, across wildly different centuries and countries, a handful of brilliant minds basically changed the world we live in. We're going to explore their stories today. And don't worry, we aren't doing this like some dusty history lesson. Think of it way more like a high-stakes detective story, where the clues are numbers and the reward is the future itself. So check this out. We're going to jump back and forth across the centuries to meet four brilliant minds who all share this exact, bizarrely specific date. We've got stops in 1768, 1932, 1961, and 1974. Four totally distinct eras, four massive leaps in human progress. Let's start the journey. All right, let's start with a bit of a mystery. Think about what you're doing right at this very second. Maybe you're watching this on a smartphone, maybe you were just scrolling through social media or, playing a game. Have you ever actually stopped to wonder how the tiny little microchips inside your phone manage to control unpredictable, chaotic quantum energy without just constantly overheating and breaking down? I mean, it seems completely impossible that such wild, microscopic energy can be perfectly tamed just so you can send a quick text message or stream your favorite song, right? Well, our first stop is May 4th, 1932. That is the exact birth date of an American mathematician named J. Edward Nelson. And his story is intense. He grew up during some really tough times, actually traveling back and forth between Italy and the US right during the height of World War II. Living through that kind of intense global instability gave him this profoundly nonconformist attitude. He had a will of steel and just flat out refused to accept things as they were. And that exact rebel mindset, that's what eventually led him to completely revolutionize physics during his time at Princeton University. He basically looked at the utter chaos of the universe and decided, nope, I'm going to organize this. The absolutely crucial point here is his biggest contribution. Nelson took the incredibly powerful tools of probability theory and applied them to something wildly complex called quantum field theory. Now, what does that actually mean in plain English? Well, imagine a giant room filled with millions of superballs, just bouncing off the walls at lightning speed in total random chaos. Now, imagine using math to figure out exactly where and when every single ball will hit a wall. That's essentially what Nelson did. He mathematically made random quantum fluctuations completely predictable. By turning the absolute chaos of quantum physics into reliable, solid rules, he helped lay the very foundation that makes our modern electronics function smoothly without just frying themselves. And this brilliantly illustrates our first big takeaway: the unpredictable quantum world tamed by math. Math is the invisible controller of literally every single gadget you own. Think about that word for a second. Invisible. You don't see the complex equations when you tap your screen, but they are absolutely there, holding the whole shebang together. Without Nelson's theoretical groundwork, the reliable tech sitting in your pocket right now just wouldn't be possible at all. All right, let's leave the 1900s behind for a minute and jump way backward. We're going all the way to the 18th century, specifically the year 1768 for our next big mystery. Think about this for a second. How do the complex mechanical gears inside heavy machinery or water pumps or high-speed car engines always turn with such perfect timing? Think about the sheer violence of gears for a moment. Massive chunks of solid metal grinding against other chunks of metal at incredibly high speeds. How do they interlock perfectly without instantly crushing each other into fine metal dust? It's a massive engineering problem with incredibly high stakes. Well, that mechanical puzzle was solved by a genius we actually lost on this exact day, May 4th, back in 1768. The French mathematician Charles-Etienne Camus. He wasn't just sitting alone in a room thinking of abstract thoughts either. He was a highly prominent member of the Académie des Sciences and actually spent his time lecturing to trainee architects. He was completely obsessed with teaching them how to build reliable structures and totally unbreakable machines in the real physical world. His real genius was in the deep, deep analysis of shapes. Camus used geometry to calculate the mathematically perfect shape for toothed wheels. He didn't just guess. He calculated the exact, precise curve a metal tooth needed to have so it could slide perfectly against another tooth without locking up or shattering into a million pieces. By perfecting clockwork design and machine mechanics and writing it all down in his famous Cours de Mathématiques, he quite literally laid the groundwork for every motor, engine, and gear system we still rely on today. Which leads us to this massive realization. Every turning gear in the world follows the strict rules of geometry. Mechanical motion isn't just about raw horsepower or metal pushing metal, it's really just pure geometric shapes in action. So next time you hear a sports car rev its engine on the street, just remember, you are literally listening to geometry at work. How cool is that? One date, so many stories. Let's keep this momentum going and jump forward from the mechanical age right to the dawn of the digital age in 1961. The stakes are about to shift from heavy metal to tiny pixels. Now, here is a question for anyone who loves digital entertainment. When you boot up a modern video game and drop into one of those massive, gorgeous open-world environments, how does your computer or your console instantly calculate and render millions of 3D colors, shadows, and textures on your screen without lagging out? How does it build entire living universes in a fraction of a second? To really understand how, we have to look at Herbert Turnbull, who passed away on, you guessed it, May 4th, 1961. He was a brilliant Regius professor of mathematics at the University of St. Andrews. But what's incredibly fascinating about Turnbull is that he was also a passionate, hardcore mountaineer. He loved climbing massive peaks, basically proving that mathematicians love conquering giant, intimidating obstacles, both in the real physical world and on a piece of paper. Turnbull mastered these incredibly complex fields that we call matrix algebra and invariant theory. Put simply, he turned complex 3D geometry into calculable mathematical formulas. If you want a basic way to think about matrix algebra, picture it as a massive mathematical grid that tells a computer exactly where to put a specific pixel in a 3D space and exactly how to move it. His extensive work provides the exact algebraic frameworks computers use today to calculate intense graphics and render digital spaces at absolute lightning speed. And here is the big reveal. The 3D graphics on your screen are just matrix algebra in disguise. Seriously, every modern video game you play, every CGI movie you watch, is secretly just doing algebra really, really fast behind the scenes. So if you're ever sitting in class and thinking algebra is totally useless, just remember, it is actually the only reason your Xbox or PlayStation works at all. Still on May 4th, we're going to make our final jump across the timeline. We are moving to the year 1974 for our last story, stepping right into the final act of our historical mystery. We've talked about the wild energy of quantum physics, the grinding metal of gears, and the digital magic of computer graphics. But here is the ultimate question. Who figured out how to teach the complex math required to build the modern internet? I mean, the math existed, sure, but teaching it to the people who would actually build our digital world was the real hurdle. How did the early pioneers of our digital age learn all this incredibly difficult math in the first place? Well, the answer lies with Marceli Stark, who passed away on May 4th, 1974. He was a brilliant Polish mathematician who lived through the absolute devastation of World War II. After the war, in a recovering Poland, mathematicians gathered together to rebuild their world and share knowledge. Stark worked during a time when, for him and his peers, discussing mathematics wasn't just a day job. It was an obsession. It was a literal fever of ideas that brought people together and gave them real hope for the future. The history here is just incredibly rich and alive. Stark's biggest contribution wasn't just discovering some obscure new formula. It was creating incredibly clear textbooks on higher algebra and analytic geometry. With his colleague Andrzej Mostowski, he completely transformed how advanced mathematics was taught to students just like you. Those textbooks, the very things you might groan about reading for homework, were the secret weapons that effectively trained the entire generation of minds that went on to build our modern digital infrastructure. It's absolutely amazing to think about. And honestly, it should leave you in complete awe. Every great app started with a student reading a math textbook. Education is the absolute root of all technological progress, and Stark was the ultimate educator for those early digital pioneers. The tools you use to connect with the world today started as mere words on his pages. So, when we step back and look at all these incredible minds across the centuries, let's tie this whole thing together. Every single person we met today, across totally different eras, different countries, and entirely different disciplines, all asked the exact same fundamental question: what is the mathematical pattern hiding inside the chaos? And because they had the guts to ask that question, our world today is forever changed. So I'm going to leave you with this final thought. The world is still full of chaos just waiting to be solved. There are problems out there we haven't even named yet. Are you the next great mathematical mind to find the pattern? Thank you so much for exploring this fascinating explainer with me today.
Keep wondering